Cardiac volumes. First, I would like to ask you. Cardiac output is the amount of blood that the heart throws into the vascular system with two ventricles or one. Which ventricle releases the greater volume of blood into the vascular system per minute? To correctly answer these questions, you need to remember the structure of the circulatory system. Since it is a closed system, the output of blood from the right and left hearts, ventricles, should be equal. Cardiac output should be considered as the amount of blood ejected by one of the ventricles into the circulatory system per unit of time, minute. More precisely, cardiac output is the amount of blood passing through any normal section of the circulatory system per unit of time, that is, flowing from the atrium to the ventricle, from the left ventricle to the aorta, from the vena cava to the right atrium, from the right ventricle to the lungs, and so on. I want to reveal a secret. The left ventricle ejects slightly more blood per unit of time than the right. What reason? If you answer that the systemic circulation is larger than the small pulmonary circulation and the pressure in it is greater than in the small circle, you will be wrong. I'll explain why. I have 2 barrels filled to the brim with water. One barrel is 4 liters, analogous to the systemic circulation, the second is 1 liter, analogous to the pulmonary circulation. I will pour an additional half liter of water into the first barrel. How much will it overflow? That's right, half a liter. I will pour an additional half liter of water into the second barrel. How much will it overflow? That's right, half a liter again. If the left ventricle additionally releases 5 liters per minute into the systemic circulation, then 5 liters of blood should be transfused from the systemic circulation during the same time. Where? To the right heart. And the right ventricle must release this volume into the pulmonary circulation. Why does the left ventricle emit slightly more blood than the right? There are shunts in the circulatory system. So the bronchial arteries of the lungs, systemic circulation, must discharge into the bronchial veins, systemic circulation, and they discharge blood into both the bronchial veins and the pulmonary veins, pulmonary circulation. So, not all the blood passes through the right heart, and the left ventricle must throw out the blood that will pass through the right heart, as well as the blood that will pass through the shunts. Normally, no more than 1% of total cardiac output passes through the bronchial arteries. The bronchial arteries also anastomose with the pulmonary arteries, with obstruction of which the shunt blood flow can increase to 18 to 30%. In cardiac physiology, cardiac output, CO, also known as heart output, and often denoted by the symbols. Cardiac output is the volumetric flow rate of the heart's pumping output, that is, the volume of blood being pumped by a single ventricle of the heart, per unit time, usually measured per minute. Combined cardiac output is the sum of the outputs of the right and left sides of the heart. It is a useful measurement in fetal circulation, where cardiac outputs from both sides of the heart work partly in parallel by the foramen ovale and ductus arteriosus, which directly supply the systemic circulation. Cardiac output is the product of the heart rate, H, R, I, E, the number of heartbeats per minute, B, P, M, and the stroke volume S, V, which is the volume of blood pumped from the left ventricle per beat, thus giving the formula. And now, you have to answer the question and write in the chat. I will look and note in the electronic journal who is present at the lecture. If there is no answer, then I will post absence. Cardiac output is the product of the heart rate, H, R, I, E, the number of heartbeats per minute, B, P, M, and the stroke volume S, V, which is the volume of blood pumped from the left ventricle per beat, thus giving the formula. The factors affecting stroke volume and heart rate also affect cardiac output. Cardiac volume, static volume, diastolic reserve, stroke volume, maximum stroke volume, systolic reserve, residual blood volume, end systolic volume, end diastolic volume, minimum end systolic volume, maximum end diastolic volume. What are static volumes? This is a volume whose measurement does not take time into account. That is, milliliters are measured. And dynamic volumes, such as cardiac output, are measured in milliliters per minute. Another representation of cardiac volumes and reserves. End systolic volume, ESV, is the volume of blood in a ventricle at the end of contraction, or systole, and the beginning of filling, or diastole. End systolic volume can be used clinically as a measurement of the adequacy of cardiac emptying, related to systolic function. Clinically, ESV can be measured using two-dimensional echocardiography, MRI, magnetic resonance imaging, tomography, or cardiac CT, computed tomography. End diastolic volume, EDV. End diastolic volume is the volume of blood in the right end, or left ventricle at end load or filling in, diastole, or the amount of blood in the ventricles just before systole. End diastolic volume. Because nearly 2/3 of the blood in the systemic circulation is stored in the venous system, end diastolic volume is closely related to venous compliance. Stroke volume, SV. Stroke volume is the volume of blood pumped from one ventricle of the heart with each beat. Stroke volume is an important determinant of cardiac output, which is the product of stroke volume and heart rate, and is also used to calculate ejection fraction, which is stroke volume divided by end diastolic volume. Because stroke volume decreases in certain conditions and disease states, stroke volume itself correlates with cardiac function. Stroke volume calculation. Its value is obtained by subtracting end systolic volume, ESV, from end diastolic volume, EDV, for a given ventricle. SV equals EDV minus ESV. Stroke volume calculation. In a healthy 70 kg male, the EDV is approximately 120 milliliters and the ESV is approximately 50 milliliters, resulting in a difference in stroke volume of 70 milliliters. Stroke work refers to the work, or pressure of the blood, P, multiplied by the stroke volume. Cardiac index, CI. It is a hemodynamic parameter that relates cardiac output in 1 minute to body surface area, BSA, thus relating heart performance to the size of the individual. The unit of measurement is liters per minute per square meter. These are the formulas for calculating the cardiac index. It is clear that if the greater the mass and height of a person, the greater his cardiac output should be. And the calculation of the surface of the human body is based on his mass and height. Therefore, the sufficiency of cardiac output can be judged by calculating it per unit of body surface, that is, by calculating the cardiac index. I think that instead of the cardiac index it is better to use cardiac output standardized, corrected, to the body surface as an indicator. Namely, cardiac output divided by the patient's body surface and multiplied by the body surface of a standard person, 1.73 square meters. Similar to cardiac index, is a parameter of relating the stroke volume to the size of the person. I think that instead of the stroke volume it is better to use stroke volume corrected, standardized, to the body surface as an indicator. Namely, stroke volume divided by the patient's body surface and multiplied by the body surface of a standard person, 1.73 square meters. An ejection fraction, EF, is the volumetric fraction, or portion of the total, of fluid, usually blood, ejected from a chamber, usually the heart, with each contraction, or heartbeat. It can refer to the cardiac atrium, ventricle, gallbladder, or leg veins, although if unspecified it usually refers to the left ventricle of the heart. An ejection fraction is widely used as a measure of the pumping efficiency of the heart and is used to classify heart failure types. It is also used as an indicator of the severity of heart failure, although it has recognized limitations. In heart failure, the difference between heart failure with a reduced ejection fraction and heart failure with a preserved ejection fraction is significant, because the two types are treated differently. The ejection fraction of the left heart, known as the left ventricular ejection fraction LVEF, is calculated by dividing the volume of blood pumped from the left ventricle per beat, stroke volume, by the volume of blood present in the left ventricle at the end of diastolic filling, and diastolic volume. The left ventricular ejection fraction is an indicator of the effectiveness of pumping into the systemic circulation. The ejection fraction of the right heart, or right ventricular ejection fraction RVEF, is a measure of the efficiency of pumping into the pulmonary circulation. A heart which cannot pump sufficient blood to meet the body's requirements, heart failure, will often, but not invariably, have a reduced ventricular ejection fraction. Let's repeat it again. By definition, the volume of blood within a ventricle at the end of diastole is the end diastolic volume. Likewise, the volume of blood left in a ventricle at the end of systole, contraction, is the end systolic volume. The difference between end diastolic volume and end systolic volume is the stroke volume. The ejection fraction is the fraction of the end diastolic volume that is ejected with each beat, that is, it is stroke volume divided by end diastolic volume. The following equations help translate the effect of F and EDV on cardiac output Q, via SV. Cardiac input C, I, is the inverse operation of cardiac output. As cardiac output implies the volumetric expression of ejection fraction, cardiac input implies the volumetric injection fraction, I, F. Injection fraction is end diastolic volume divided by end systolic volume. Cardiac input is a readily imaged mathematical model of diastole. Example cardiac values.